Hey classes, welcome back. We're going to go through everything from a little bit of the Led Zeppelin today to a little bit of your very first chemical reaction, at least in here, to revisiting an experiment you probably did with Mr. Leek or Miss Miller last year. So let's jump on in, try and keep it to 10 minutes if we can. First of all, a little bit of housekeeping. Don't forget, take the quiz that is out there this afternoon, later this afternoon. There's also an optional makeup quiz. If you've missed for any reason, any of the first three that we had, that is your way to make it up. I offer 2 of those per trimester, and if you have any zeros in the grade book on a quiz, there's your chance to get it. Also, the lowest quiz of the trimester gets dropped. Okay, back to the lesson here. Let's see if we can squeeze it all into 10 minutes. We started talking about water. How does that relate to Led Zeppelin? Well, we talk a little bit about chemical reactions today, and you might have seen that album cover that you could just barely see off the screen right here. We started talking about that because that was the famous picture of the Hindenburg when it burst into flames. Now, a little bit of a history lesson on the Hindenburg. That was filled with hydrogen instead of helium. Helium gas, as you know, is used in party balloons all the time now. If a party balloon with helium gas in it gets too close to the birthday cake and the candles burn the balloon, it pops and the helium floats away, and that's that. If you had it filled with the lighter hydrogen gas, you'd be blowing birthday cakes up all over the place. Not a really good thing to have around a birthday candle. Why did they fill it with this? This was just prior to World War II. A lot of people in the United States had the clue that we probably would be fighting Nazi Germany one of these days, and they were not selling helium to Germany at that time anymore because they did not want to do anything that might possibly aid Germany's war effort. And so Germany at the time said, well, fine, we'll fill our new Zeppelin blimp with hydrogen instead, which is technically lighter for a given volume than hydrogen gas, helium gas, but as you know, it's very, very, very explosive. And we'll get to that in just a second. But not a great idea when you're talking about being able to keep a blimp from exploding. They wanted to make sure that it was safe. What probably happened, we'll never really know. There's probably a small leak somewhere that was ignited by some static electricity. Whatever the case, we saw a dramatic example of a chemical reaction there that exactly fits into one of the chemical reactions that we're talking about in this class, which is water, or one of the molecules we're talking about in this class. So going on through this, water, from our brain pop, is a compound. It's made with hydrogen and oxygen, of course. And we call it the universal solvent because it's great at dissolving things. The video talked a tiny bit, the brain pop at the beginning, about how sometimes water can taste different in different places. For example, I grew up in Millbrae, right over the hill here, right next to San Bruno. My aunt and uncle who lived right across the border over in San Bruno. We'll talk about this in more detail when we talk about the water delivery system here in California. Basically, though, San Bruno, and I had the opportunity to tour it a couple of years ago, gets their water from well water, these big wells that pump up the water, and they hold it in these storage tanks right over there by the San Bruno train station. Millbrae gets their water slightly differently, almost directly from the Hetch Hetchy system. Again, we're going to learn all about that this year. Just picked up a great book from one of my students, thank you. And when you look at the Hetch Hetchy water delivery system, the well water that San Bruno gets their water from picks up a lot of minerals on the way to the tap, whereas the Hetch Hetchy system, not quite so many. So even as a kid, I could always tell the difference when I went over to my aunt and uncle's house, or Lena Dennis's house. I could always tell their water tasted different than our water just a few blocks away. And I didn't know at the time, but it had to do with our water delivery system and water's unique characteristic of being a universal solvent, meaning, and we're going to talk about the why of that, it can pick up minerals and carry them long distances. One of the things that we tried to give as an example of this is I had students, if they wanted to, pull out their phone and only use the compass app. Now, on most phones, they have a little compass. This is my magnetic compass right here. And if you look at my magnetic compass, it points to magnetic north, not true north. If I'm looking at magnetic north, that's an example that most 7th graders have seen that, hey, we have a north pole, a south pole. Compasses orient themselves along those lines. And just like our planet has a north and a south side, if you will, our molecule, our water molecule, has a positive and a negative side. We'll talk about that in the next slide, but if you look at this down here, we had a couple of molecules. Now in 8th grade and high school, we get much more into detail, although I'm more than willing to go through it with anyone who wants to, spend a little extra time on this, on why certain atoms bond or combine with other atoms. But check out this one right here. Using our color scheme from yesterday, we have 2 oxygens and a carbon, the 2 red ones and the black one here, combining to form carbon dioxide. A single type of atom can bond to, itself, if you will, in terms of the same type of atom. Look at this. We have 2 oxygens here stuck together. That's O2. We don't call it an oxygen atom anymore. Now it's called an oxygen molecule. And in both of these cases right here, the molecules have no polarity. They've got no extra charge to them. But if you look, and I'm going to try and spin the board here in just a second. If you look over here at, pull these across, the picture that was on the other side of the board here, as I spin and try and stay within the bounds of my little microphone, the picture that we had on the board has a water molecule. Again, hydrogen. We're coloring hydrogen blue this year. All year long when we draw molecules, we're coloring hydrogen blue. Water has a plus side and a minus side. Now, for now, we just need to know that. To go into a little bit more detail for those students who want it, it turns out those electrons that we learned a little while ago about, they tend to spend more time, if you will, down around the oxygen side. The oxygen pulls on them a little bit more. But regardless, that plus and that minus is not unlike the plus and minus that you can see with our own planet right here with a compass. And that plus and the minus does a lot of things that make water vitally important for life. One, as water freezes, these little pluses and minuses line up. And usually, as molecules lose kinetic energy and they go to the solid state, what happens is they get more dense, but water does this really special thing where it gets less dense as it turns to ice, water ice. As it freezes, it's a little bit like having a bunch of people all in a dance, being close together, moving around. They've got a lot of kinetic energy. As they lose kinetic energy, it's almost as if, and to carry the analogy to the water molecule, you have them stiffly hold their hands out, and all of a sudden they have to hold hands with the person next to them very, very stiffly. The water spreads out just a little bit as it freezes. This also gets to the point too when we're talking about global warming, climate change, the oceans rising. Part of the reason that the oceans are rising is, yes, you have ice that is on land right now in the form of glaciers melting and pouring into the oceans. But the other reason that the water is rising is because as the kinetic energy of the water rises again, as the temperature goes up, the average distance between the water molecules increases a little bit. Again, using the dance analogy, it's like having a lot of people all of a sudden moving, a faster paced song comes on and everyone's moving a little bit more than they were a few moments ago. They generally tend to spread out a little bit more. The average kinetic energy of each water molecule speeds up, and that increases the volume of water. That's the main reason that the oceans rise when we talk about global warming. When we check out the other things that we brought up, we had a couple pictures here online just to give examples from movies, examples like that. We also had the students drop as much water as they could onto a penny, the classic experiment. That gets over to what Mr. Leek and Miss Miller did across the quad there last year. And let's see if we can pull it up here on the screen just over to my side. It'll have some writing over it, but I used a clip, and even if you've never seen the movie, I actually haven't seen the movie, but I did see this clip, and I know about the movie. It's called Passengers. And a character played by the actress Jennifer Lawrence, she gets into a swimming pool, and in this particular case, let me turn this off for just a second. The swimming pool is supposed to be in a ship, and the ship in space is spinning. Now, spinning gives the illusion of gravity. It's not really gravity, it's a different force. But just like my coffee cup right here, which has coffee in it, I can spin it really fast, and if I spin it fast, the coffee doesn't fall out. In the movie, they show Jennifer Lawrence's character jumping into a swimming pool in the spaceship that's spinning. While she's swimming, something goes wrong with the spaceship. It stops spinning. If that were to really happen, they do a good job with this particular movie, at least on this clip, showing the water kind of sloshing out of the pool. She would basically be surrounded in a sphere of water. There'd be no up. It would be very, very dangerous or difficult to swim out of something like that. On a more real life example, we then showed water in the International Space Station. And water at the International Space Station, when they pour it out, makes a perfect little bubble, a perfect little sphere. And that makes sense if you think about, again, get my glasses on here, looking at the polarity of the water molecule. It tends to be a little bit like if you had a bucket full of magnets, and all the magnets were little tiny bar magnets, and you reached in and you try to pull out a few, it would tend to clump into something that looked like a sphere. Water does that. To put it another way, you know how people classically draw a raindrop as being kind of thin at the top and it kind of goes out at the bottom? Well, it's not the case. A raindrop generally is spherical in shape, and as a matter of fact, if they get large as they start to fall, it's a sphere with like a little flat part on the bottom as it falls because of the air, the friction that it's running into. The point is, the main takeaway is all these different examples were designed to get across the idea, from dropping water droplets on pennies, from drawing the water molecule on the board, from showing a clip from the space shuttle and a clip from Passengers, the movie. All of this is designed to get across the idea that the water molecule is special because of its polarity. It has that polarity because of its shape. It's a little bit lopsided. We always call it all year the Mickey Mouse molecule. It's got the hydrogens on one side, the oxygen over here, and again, the oxygen tends to hold on to those electrons just a little bit more than the hydrogens do. And so the overall effect on the water molecule is that it has this opposite charge that makes it critically important for life. Remember, if it wasn't for this polarity, water on our planet would freeze like in oceans and lakes from the bottom up. Instead, of course, starts freezing at the top and works its way down. That one fact about water makes it critically important for life, not only here, but when we look at the James Webb Space Telescope, we're looking for places that might have water in deep space, because that would be a really, really good indication that there's at least a good possibility for life there if it's got some other conditions as well. Moving on to the stuff that we need for class, we had a little bit on, let me spin this way, we had a little bit more video clip on water from Ian Stewart, really only about 2 or 3 minutes, where he was showing really there's not that much water on our planet. Yes, 71% of our Earth's surface is covered by water currently, but if you were to take all that water and combine it into one ball in space, it shows this really relatively small amount of water on our planet. And when you're looking at, finally, our biosphere, this is where it tied in with the current environmental challenge of global climate change, global warming, because global warming isn't just rising oceans because of melting glaciers. It's rising the oceans because the average distance between the water molecules is increasing as we increase the temperature. So that's where I'm going to leave it today. Just a quick reminder. Remember, covered a lot, but you're really responsible for what's on the board, the things that are in our notes. Don't forget to take today's quiz that is out there all the way through Saturday. And if you've missed any of the first, second, or third quizzes, there is an optional extra credit quiz that will be out there this evening. And again, that will be open all the way through Saturday at 11:59 p.m. Although you have time to take it here in school during the week, I just keep it open a little bit longer for any students that might have extra circumstances where for some reason I can't get to it here at school. So 11:59 p.m. on Saturday is the time to take those extra credit quizzes or the makeup quizzes. Have yourself a great Wednesday. I'll see you in class and online. Take care. Bye-bye.